Hi guys, we're going to move into the second chapter on constant acceleration. We're going to just look at the graph forms for it first. There's three sort of graphs that we need to worry about and how we can actually use one graph to draw another one. We've got what we call displacement time graphs, ST graphs. Sorry about the cat, it's being a pain at the moment. So a displacement time graph, or an ST graph, is actually something you recognise as being up the side the displacement or distance, moving across the side the time. S, as far as I can remember, is space. It talks about space. The language we use consists of a number of letters. We've got displacement, and displacement is a form of distance, but it involves a vector distance. So if you go on a journey out and then come back, displacement is actually the distance from your starting point. So in this case, what we've actually done on this journey is a displacement graph where we started off at 0, we've slowly moved away to a point, and then we've come back. And that's a displacement graph for this journey over a period of time. So S is space. U and V are both velocities. And U is initial or start, and velocity is end or current. And we often wind up having to use other variables in more complicated situations. If we want the initial displacement, people often write things like S0 and V0 for a displacement, initial velocity. Acceleration is a variable we often use as well, and that's the variation of time. Oops, sorry, 1L. I keep doing that. So acceleration, and that's the change in velocity in a time, and T is the time component. So altogether we talk about these being suvat. And we will, when we come to doing the calculations, I'll be doing suvat notes. We'll write suvat out, put things in, find out what we want to do. And it helps us choose which equations to use, but for the moment we're not using equations. So the displacement, if everything's along the bottom, the object goes nowhere. No journey at all. And we're staying at home. If my displacement graph stays a fixed distance away, still no journey, or a journey in, this is a distance here, oh, missed off the S. So we've got some displacement, it's known journey, but away from time or origin. Now, technically, because we're talking about displacement as a vector, some people sometimes think this could be a particle moving in a circle, but displacement in that case would actually be a sine wave because it's going to contain position x and y directions. You would actually have two components. This really is a vector and should strictly have an arrow on top. So should the first four of these. Vector quantities. Okay. At the moment we're only talking about one-dimensional movement anyway, so in this case there's no journey and there's no such thing as a circular motion. And then we start getting interesting when we start doing movement. as we set up here. I could start off at home, go on a journey somewhere, and that means there's a journey as I'm moving away from home. And the journey is going to be, if you actually think about S and T, at any point, S over T is a distance over time, and that's the average speed or velocity. Let's say velocity for a moment. At this point. Okay. If you do the gradient of the graph, there, if you calculate the gradient, it looks like ST for this version, but this would actually lead to being the velocity at this time. Okay. So the point, if you do S over T, that's your average velocity or average speed at the time. If you do the velocity S over T, that gives you a point and calculate its gradient, that gives you the velocity at that instantaneous point in time. So one other variation on this is what happens if we have varying velocities. So let's draw a quick velocity time graph and see how that impacts on the so this one, the velocity here, the average velocity in the instantaneous actually leads to a velocity time graph for this one, which is constant. It's moving at the same speed all the time. And that's by looking at the gradient. Okay, now let's look at a velocity time graph. Actually, if I use Z for velocity, it will help keep the graphs different. So if my velocity graph starts at 0 and moves steadily increasing, we need to think, what's this gradient saying about the distance covered? Now, if you actually remember a little bit to do with calculus and where it comes from, area under a graph is actually the same as finding an integration or finding the value before. So that this gradient here, is constant, and the gradient under this, the area under this graph, is what gives me the displacement. So going that way, if we calculate the area, it will give me the displacement. So here we're going to take the area under the section, and that will give me my displacement. So let's draw the displacement. So for a constantly increasing acceleration, what we get is a displacement which starts off small or nothing and increases by a small amount. Next section increases by a larger amount. So now we're looking at an increase. And all the way up, what happens is we start increasing, and you get a curve right, as it accelerates. So velocity increasing, if it's increasing steadily, that's a constant acceleration. And what you see in this is a curve turning up. Let's flip it and see what happens if we have a velocity that decreases. And for this one, I'm going to start at a distance. So I'm going to have to start with somewhere else. Usually no, I won't do it, just do it that way. So we've got V, we've got T, and we've got S, and we've got T. So this time I want my start off high and reduce. And in a minute we'll actually even continue on afterwards and see what that does if that goes the other way, low. So we start with a high speed, so the gradient is quite steep. Each section, steepness falls away. So what eventually happens is at this point here, the gradient is horizontal. So this is a deceleration, and if we were to continue afterwards, it would then start coming back towards. Just try and keep it moving in the same way. So this velocity is decreasing, which is a deceleration or braking or retardation. So deceleration, braking or retardation leads to a decrease in velocity, and that leads to a curve going the other way. So it starts off steep, shallows out, and if the velocity goes negative, it means that the displacement is now returning towards this zero. Okay, so the velocity increase. At the moment, all we're going to worry about is constant acceleration. So the acceleration in both of these, it's one value. You're not going to be asked for an acceleration graph. That's going to be something different in M1. So in this case, the acceleration was below the line. And that's the situation we're in, is we've got constant acceleration. This model, you might suddenly realise, is actually what happens if you were to throw a ball in the air. So if I was to take a basketball, throw it in the air, there's my S versus T, although that's the real time. If we ignore horizontal velocity, we actually have here a curve for time, so the displacement can start slightly higher, that's my S0. As time goes along, the displacement gets higher, but slower, and then starts coming back down. I should have done that last thing in blue. So this is acceleration, a basketball under gravity. So that situation leads to a velocity graph. V2. Velocity starts off quite high because it's increasing, steep. Then over time it gets to this point here where it's no longer rising and it stops. So instantaneously that's no longer let's change it to red again. this point, it's no longer rising, the velocity is 0. And then here we're falling. Okay, start rising, max height stationary, or vertically stationary. Still got horizontal motion, and then we've got falling on the right. And this is assuming, which we normally do, positive direction is up. We're falling under gravity. Gravity is acting downwards with the value g. Remember, most of the time we're using g is 9.8 meters per second squared. Which leads us to the acceleration graph. And this is g. G working downwards is 9.8. And that's a horizontal line, causing that velocity